evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy here at Foothill College in Los Altos Hills, and I'm very pleased to welcome everyone here in the Smithwick Auditorium and everyone watching us on YouTube to this talk in the 24th Annual Silicon Valley Astronomy Lectures. This series of popular free lectures at Foothill College is co-sponsored by 3 different organizations, all of them devoted to astronomy education and outreach: the Foothill College Science, Technology, Engineering, and Math Division, the SETI, or Search for Extraterrestrial Intelligence Institute, headquartered in Mountain View, and the Venerable Astronomical Society of the Pacific, which has been doing educational outreach in astronomy since 1889. This particular talk is also co-sponsored, I'm pleased to say, by Stanford's Kavli Institute for Particle Astrophysics and Cosmology, because our speaker is a Stanford professor, and we're delighted to have their cooperation in publicizing the lectures. All right. So let me now, without further ado, introduce our speaker. Our speaker is Dr. Laura Schaefer, who is an assistant professor of Earth and Planetary Sciences at Stanford University. She's a planetary scientist who focuses on how gases and rocks react with each other to form the atmospheres of rocky planets, both inside and outside our solar system. She's particularly fascinated by lava worlds and the volcanic moon Io, one of the moons of Jupiter, as well as the distant past of planet Earth and the past of its neighbors, Venus and Mars. Tonight, Dr. Schaefer is going to tell us about the many roles of water in making planets habitable, both in our solar system and elsewhere. Ladies and gentlemen, it's a privilege for me to introduce Dr. Laura Schaefer.
Great, thank you, Andy. It's a pleasure to be here to talk about some of the research that my group at Stanford does. And so my training is both as a planetary scientist and as an astronomer. I work on exoplanets, but also planets within our own solar system. And as Andy mentioned, a lot of the work that my group does is to understand the origin and evolution of planetary atmospheres. So today I'm going to focus really only on the effect of water on planetary habitability. Now, a disclaimer, I am not a biologist, so I can't tell you why life requires water. I'll maybe touch on a couple of reasons that biologists have proposed for that particular question, but I'm going to focus really on how water affects the environment of planets, the surface environment where we think that life is going to be found. One of the reasons we focus on water is just that water is really abundant. Hydrogen is the most abundant element in the universe, as most of you are probably familiar with. Oxygen is the 3rd most abundant element. It's produced in stellar nucleosynthesis abundantly. But if you can see from this pie chart, oxygen is a tiny fraction of the total amount of hydrogen in the universe. Now, we have the 1st and the 3rd most abundant elements in the universe. If you look carefully at your program at the talk announcement, which I wrote myself, by the way, I was very shocked and displeased to find that I made a typo in that program where I called oxygen the 5th most abundant element in the universe. And this is out on the internet. I hate putting mistakes out on the internet. So if you're here watching this on YouTube, I apologize, but I've already corrected it in the comments, so you don't have to. But getting back to water, so if we took all of that oxygen and combined it with hydrogen, we'd still have plenty of hydrogen left over to make our stars. But in fact, that's not exactly how the chemistry happens in interstellar space or in planet-forming regions. Most of the oxygen actually combines with other elements, specifically silicon. So this is now the pie chart showing the elemental abundances in the Earth itself. Oxygen is the most abundant element in the Earth. People are often surprised by that fact. But oxygen combines with silicon to make most of the minerals that make up the rocks that make up the bulk of our planet. Those silicon and oxygen then combine with some other elements, especially magnesium and calcium and iron, to make all the minerals that make up the crust of the Earth that we live on and the mantle of the Earth that is deep beneath our feet. But looking back at water, so in addition to being abundant, that means that water is found everywhere that we look in space. This is an image of a galaxy from the Hubble Space Telescope. I'm not a galactic astronomer, so I can't tell you much about this, except that most of the emission that we see from this galaxy is actually from the water vapor in the gas surrounding the supermassive black hole at the center of that galaxy. What is a maser? A maser is basically a microwave laser. So it's not beaming light towards us because there's no optics out there in this galaxy. But essentially, the physics of this emission is very similar to how a laser operates. Water is also everywhere that we look in the solar system, especially in the outer solar system. This is, I think, a really, really cool image taken by the Cassini spacecraft, where what we're seeing in the center of this image is Saturn's rings. Here's another view of those rings, and the rings of Saturn are made almost entirely of pure water ice. Very small particles, and it's a very thin structure, possibly made by the disruption of a small moon that got too close to Saturn's gravitational field. If we look back at this image, the object in the foreground is Enceladus, which is a small moon of Saturn, and it's famous for having these geysers of water coming out of its south pole, probably due to extreme tidal heating of its interior. The surface is made of water ice that's very distorted, and under that water ice, a few kilometers beneath that, is probably a global ocean of water. In the background, looming kind of ominously in the background of this first image, is Titan. Titan is the largest moon of Saturn. And you might not actually associate water with Titan if you know anything about its atmosphere. Its atmosphere is mostly nitrogen and methane, actually. The Cassini mission actually had a lander that it sent to the surface of Titan. This was the Huygens probe. And these are images that were taken on the way down towards the surface of Titan. And all the black regions in these images are actually liquid on the surface of Titan. But that is liquid methane, not liquid water. Lots of hydrocarbons covering the surface of Titan. But again, deep under the surface of Titan, this is a model of what we think the internal structure looks like. There's the organic-rich atmosphere and surface, but beneath that, beneath the crust, we think the crust is largely made out of water ice again, and below that is potentially another subsurface water ocean. So we see water also in the inner solar system. Mars, of course, has water at its polar caps. NASA is happy to announce many times that it has found water on Mars in various locations. There is probably water in much of the regolith in various locations on Mars at the present day. And it may once have had liquid water on its surface back in the past, but it doesn't at the present. We even find water on the innermost planet in our solar system, Mercury, which is the hottest planet in our solar system, also one of the smallest. There is, in fact, water at the polar regions of Mercury, tucked into the deeply shadowed regions of craters that never see sunlight. The yellow color here in this pop-out image is a radar detection of water ice in those craters. So we see water everywhere, but really the Earth's surface water is pretty unique in that we have liquid water on the surface in contact with an atmosphere that is thin enough to see through so we can see that ocean from space, right? And so far in our experience, we have found thousands of planets outside of our solar system so far, exoplanets or orbiting other stars. But none of them, so far as we know, has water on its surface like this. We're still looking for that one special planet. Maybe we found it, but we don't have the evidence of water on the surface. And that is really one of the goals of exoplanet astronomy, is to find a planet that looks like this. And although this water on the Earth covers about 70% of our surface, that water actually only makes up about 0.02% of the total mass of the Earth. That's a tiny fraction of the Earth's overall mass, and yet it has an inordinate effect on the environment in which we live ourselves. And if we compare that amount of water to those objects that we were looking at in the outer solar system, including the icy moons like Europa and Titan over there on the far right, in this image, we see the size of the object relative to the size of the Earth, and then in a small blue sphere next to them is the volume of water. For the Earth, that's the water on the surface, and for Titan and the others, it's the combined total water we think they have. And so you can see that Titan, in fact, has substantially more water, at least than Earth has on its surface. Right? So all of these objects, especially these objects in the outer solar system, are very water rich. But I think this is actually a little bit misleading because this is not representing all of the water that Earth has itself. So if we look at another version of that kind of info diagram, again, we have the Earth, and we have a naked Earth where all the water has been collected into that little sphere. So you can see sort of the relative volumes of the Earth to the water on its surface. But this is actually less than half of the water that Earth actually has. So where's the rest of it? Well, if we look at a diagram of the internal structure of the Earth, the layers, we divide the Earth up into different layers. So we live on the crust layer, which in this diagram is actually thinner than the outline of that right-hand side of the diagram. And below the crust is the mantle, which we divide into a couple of layers, the upper mantle, the transition zone, and the lower mantle. And this depends on the mineralogy of those layers. And then below that is our core, which is made mostly out of iron-nickel alloy. And we divide that also into two different layers. The outer core is a liquid layer, and the inner core is solid metal. So if we say that we have one ocean mass, we use the amount of water at the surface as a unit of mass, and we have one of those at the surface. Then in this layer of the mantle, within the whole mantle, we think we have at least half of that mass, up to potentially 7 times more than that. So 7 potential oceans inside the Earth's mantle, and more even within the core. So what is the form that this water takes? Are we expecting sort of swimming pools or lakes of water in the mantle? Well, no, we don't. The water is actually stored within the silicate minerals that make up that layer of the mantle. And in fact, it's stored in what we call nominally anhydrous minerals. These are minerals that don't actually have water or hydrogen in their chemical formula. So the figure on the left over here is showing a vertical profile through the layers of the Earth, and the green bars are showing the potential water storage capacity of those different layers. So this is sort of a hypothetical, how much water could we stick into these layers if we could completely saturate them? The minerals that make up the upper mantle, the main minerals are olivine and pyroxene. So olivine is just 2 magnesium atoms with a silicon atom and 4 oxygen atoms. And olivine is the dominant mineral in that upper mantle. You can see it doesn't have hydrogen or water really in its chemical makeup. But those atoms, those elements that make up olivine, they make a crystal lattice that takes a particular pattern and it repeats at an atomic level. And water basically hides into the spaces between those atoms that make up the chemical formula of olivine. So it's hiding in what we call interstitial spaces, spaces between the atoms in the crystal lattice. You can see that bar for the upper mantle, it increases as we go down with pressure. We think as pressure increases as we go deeper into the upper mantle, olivine's storage capacity for water increases. And then there's a layer called the transition zone. This is where that olivine mineral actually goes through some phase transitions. The pressure squishes the olivine into a different shape that actually becomes more accommodating of water than the lower pressure form olivine. And so there's potentially several oceans within that transition zone alone. The lower mantle, again, we're going to higher and higher pressures and our minerals get squished further, and we think that there's less capacity to store water in that lower mantle. Now, how do we determine these water storage capacities? Well, that's done experimentally. So I have colleagues that do this kind of work. They take diamonds, very synthetic diamonds, that they squish together, and they put a little tiny sample of mineral between the two faces of the diamonds and squeeze it to try to simulate the pressures that we get at these great depths within the Earth's interior. And they put water in this sample, in this diamond anvil cell with these minerals to see how much water they can squeeze into these minerals. And that's where these estimates for how much potential water we could store in the mantle is coming from. Now, the actual amount of water might not be exactly that because the mantle might not be fully saturated with water. And so there's sort of disagreements among scientists about exactly how much water is in this interior. I've got a table there with a couple of scientific references where people have given different estimates on the amount of water that might be in this mantle layer. So they range from half an ocean mass up to 7.4 ocean masses. So you can see that there's some disagreement there. So this is the diagram here on the left showing us the potential capacity of these minerals to hold water. So how do we get from there to those actual estimates of how much water is actually in the mantle? So how do we know how much is there? And the way we do this is to try to look at actual samples of the mantle. Now, we can't actually go into the mantle. The deepest hole humans have ever dug does not even penetrate a third of the way through the continental crust. So we've not even gotten anywhere close to getting into the mantle ourselves, but sometimes the mantle helps us out and brings samples up to the surface for us. So that is usually happening through volcanism. Volcanism brings material from deep in the planet's interior up towards the surface. And sometimes minerals survive that journey, and particularly hardy minerals like diamonds can survive that journey. So diamonds form at high pressures. In this diagram on the bottom right, diamonds are forming sort of in the lower mantle, and what happens is they trap minerals inside of them as they're growing in the lower mantle, and then they get swept up in an upwelling region that is bringing material back to the surface. So this diamond here, this is a photograph of a diamond. And usually if you're going out and buying diamonds, you don't want a diamond like this, right? But scientists love this diamond. Those little black specks in it are a mineral that we have never seen on the surface of the Earth before. What happens is the diamond actually traps the mineral that formed at high pressure in its high pressure state. If the mineral just came up to the surface on its own, it would actually decompose into its lower pressure state, and we wouldn't actually be able to see what it looked like deep in the mantle. But so we have these minerals within these diamonds, and we can analyze these minerals and look at the amount of water that they might contain within them. And this is one of the ways that we get estimates of the amount of water in the mantle. And in fact, there was a recent study within the last year or two that found not just water, not just silicate minerals here that were containing water, it actually found a high pressure form of ice. inside of a diamond from deep in the mantle. This is a diagram over here on the right, is a phase diagram showing the different phases that ice goes through as pressure and temperature change. Most of the time, we live down in the bottom half of this diagram, right? That's where we experience pressure and temperature, is where water can go from solid to liquid to vapor. But as we go to the top of that diagram, that's as we're getting deeper and deeper into the mantle. And so the mineral that we found in this diamond was ice 7. So we do know that there is water in the mantle, and this helps us estimate exactly how much there is. Other ways of measuring the water abundance in the mantle is through lavas. The lavas are also sourced from material that comes from deep in the mantle, material that is hot relative to its surroundings, and the mantle becomes thermally buoyant, and it rises towards the surface of the Earth. When it gets to the surface of the Earth, it now still has that very high temperature, and it starts to melt. So by looking at the composition of lavas, we can learn something about the composition of the region in the planet where that lava originally came from. Particular regions, there are many different kinds of volcanic centers on the Earth, there's a particular kind of volcanic center that is particularly good for probing the deep Earth, for the very lower mantle. And these are things like ocean islands, like Hawaii and Iceland, which are, we think, fed from deep in the mantle by what we call a mantle plume. So this is a hot upwelling coming from probably the lower mantle, maybe even the core mantle boundary at the very bottom of the mantle. And this material comes up, and what happens here, the reason we have a chain of islands in Hawaii is that the Pacific plate is actually moving along the top of that plume. And so the plume is relatively stationary, and we end up with a sequence of volcanoes that become dormant as that plate moves away from the hotspot. But we can look at the composition of lavas coming out of these volcanoes and measure the water concentration in them and use that to infer something. Although it's a little bit indirect, we can use that to infer something about the source in the mantle. So we also think, in addition to having water in the mantle, we also think that there is probably the potential capacity to store a huge amount of water actually in our metallic core. So again, the left-hand diagram here is the storage capacity, and you can see that the core has the largest potential storage capacity of any layer within the Earth. And this pie diagram over on the right is showing at least one person's estimate of how much water that the Earth has and the reservoirs is just distributed between. And they put the number of water oceans in the core at about 12. So 12 times the amount of water on the surface within the Earth's core. Now, when we as planetary scientists say there's water in the core, I have to put that in finger quotes because what we actually mean is hydrogen. So it's hydrogen that dissolves in the metal alloy. We call it water because we think it was originally sourced from water that the Earth accreted. So there's a potential for huge amounts of hydrogen or water to be in the core, right? So combining these estimates, right? If we have 7 oceans of water in the mantle and 12 oceans of water in the core, right? We have almost 20 oceans of water on the Earth total, 20 times what we see on the surface today. So where did Earth get all of this water? Well, the planets in the solar system and planets around other stars, they form in a protoplanetary disk around a young star, right? So the star itself is forming at the center of this disk, and material is funneling through a disk onto the star. And the planets form out of the solid materials that are floating around in this disk of gas and dust that's orbiting the star. And in this gas, the gas is largely hydrogen and helium again, but there's oxygen and carbon and all of the other elements that make up our planets. All right, and those condense and form solid phases within this disk. there is a temperature dependence within the disk. If you're closer to the star, you're hotter. And so the further away from the star you go, the more things can condense, right? Different materials have different condensation points, or points at which they will go from the gas phase into the solid phase. If we look at this diagram is showing a sort of a cross-section of half of a disk with the star on the far left-hand side. And we can see that there's solid little particles at the middle of that disk, and the outer region is labeled ice reservoir, right? So the further out you go, the more water-rich and the more ice-rich this material becomes. And so this is a video showing sort of a simulation of what that might look like if we could get up and close and personal with this. So here we've got the star forming at the center of this cloud of gas and dust, and we've got these little tiny particles. They start off very small, and then if we're far enough away from the star to have a cold enough temperature, that ice starts to condense onto those grains that are mostly those silicate minerals that make up the Earth, and we get those ice grains starting to coat that silicate material. And what happens is those grains will start colliding together and growing bigger and bigger, and eventually those will end up becoming either the core of a planet or potentially found within some kind of gas giant planet. So let me move forward then. So how did Earth get its water then? So I'm sorry, if I go back to this diagram here, in the diagram in the bottom right-hand side, you can see that the Earth, which is at 1 astronomical unit, is inside the region where that ice would be forming, right? We're too warm where the Earth forms for ice to form. So how did Earth then get water if water is not forming solids in this region? Well, what we think might happen is that as the other planets in the outer solar system are growing, particularly the giant planets like Jupiter and Saturn, what happens is that they scatter objects inward where it can impact the growing planets in the terrestrial planet region. So I'm going to show you a couple of snapshots of some planet formation simulations where the two black dots here are Jupiter and Saturn. Saturn's the one further from me. And the colored dots are small asteroid-sized objects, and they're just colored based on where they originated. So what we think happens is that as we move further away, those objects become increasingly water-rich. And if those objects end up in this region of space where above this dashed line, this is where they might end up in Earth-crossing orbits, and they could potentially get accreted or impact onto this growing Earth. And so if we move forward in time, you can see that Jupiter and Saturn are getting bigger in this simulation, and it's their gravitational effect that is causing this scatter in the objects. Many of them get accreted onto those growing gas giants, but as we move forward in time, many of them get scattered inwards towards the terrestrial planet growing region. So you can see many of those are even that light blue color that represented those objects that were probably the most water-rich. So this is one idea of how Earth got its water, is that ice-rich material from the outer solar system got scattered inward, and Earth accreted these sort of solid bearing solid objects bearing volatiles. Another more recent theory, this was actually proposed a while ago but has recently been revived, is that in fact maybe the water that we have today was actually created by chemical reactions on the growing Earth. So as the Earth is growing through collisions of progressively larger objects, there is a lot of heat generated, and we think that the planets are potentially molten or liquid throughout them. They've melted all the rocks in the middle. So in this diagram, what's happening is we have a proto-Earth planet that has a sort of a liquid silicate mantle that's in contact with a hydrogen atmosphere. So the planet has gravitationally pulled some of the hydrogen gas out of the disk into an atmosphere around this planet. And in this model, what happens is that hydrogen gas reacts with some of the components in that silicate liquid, especially the iron oxide, to make water vapor through this reaction down on the bottom. And that, because the hydrogen is stealing the oxygen from that iron oxide, it then creates metal, and that metal then sinks into the core. And so as a result of this process, what might happen is that we end up with, we can get some hydrogen into our core to make up that reservoir that we think is there. We produce water that gets distributed throughout the mantle, and some of it gets outgassed into our atmosphere and makes our first ocean. So this is a model where the Earth didn't have to get all of that water from ices from the outer solar system, but might have actually created it in situ through these chemical reactions. So there's many other theories for how Earth got its water, and I don't want to go through them all now. So what I want to switch to is now thinking about how has this water affected the evolution of Earth as a planet. And there's many, many ways in which this has happened. I'm going to touch on 3. And so I said I wasn't going to talk about biology, but I am going to talk a little bit about life in the beginning, because it is one of the things that makes the Earth so unique. And then I'll talk a little bit about how water affects tectonics, and then finally about how it affects climate. So I don't think it's hard to convince people that water isn't crucial for life. Water is crucial for life in many ways. One of them is as a habitat, right? We have, this is a beautiful image of a river with all these beautiful trees and plants growing around it. And the water itself is, of course, a habitat for marine and freshwater organisms that we're not seeing in this image. But I'll talk a little bit about just 2 sort of ways in which water is chemically very interesting and potentially key for the biochemistry that makes life on Earth happen. One of those is that water is a polar molecule, which makes it sort of an ideal solvent for many of the components that make up our biochemistry. So by polar, I mean that water has sort of an uneven distribution of the electronic charge at the molecular level. And the reason for that is that we have this big oxygen atom, and the 2 little hydrogen atoms, they form sort of a kind of an interesting angle with the oxygen atom, and that sort of concentrates the positive charge on one side of the molecule, and the negative charge from the shared electrons of this molecule ends up sort of concentrated on the opposite side. And so that gives water a unique structure, and it allows it to also dissolve many things. So it readily dissolves ionic species like salt. Sodium chloride dissolves very easily because of the polar nature of water. But many organic molecules are also slightly polar, which helps them dissolve into water as well. Water is sort of an ideal medium to allow biochemical reactions to happen because it allows us to concentrate them in a way that a solid and a gas really don't allow. Water is also crucial for other aspects of biochemistry, and again, I'm only going to touch on a few of those. One of the major ones really is membrane formation. This is what allows us to have cells that are separated from the exterior environment. Cell membranes are made out of molecules called lipids, which have a hydrophilic head, the blue ball there, and a hydrophobic tail that dislikes being surrounded by water. And so these naturally assemble into sort of 2 layers where the tails face each other. And so we have water being acceptable on the outside layers of these cells. And so this allows us to create environments where we can concentrate water with good biomolecules on the inside and exclude other materials on the outside of that membrane. Water also helps with protein folding. Proteins have to take a particular shape to do their function within a cell. And many of the components in a protein, it's a very long organic molecule, some of those components are hydrophobic and some of them are hydrophilic, and so that really helps it take its structure and the structure that's really essential for its functioning. So there's many other ways in which water is crucial for life. And as a non-biologist, I'm not going to go into anymore. So I'm going to switch now and talk a little bit about how water affects the tectonics of our planet. Water has a profound effect on the geology of our planet. This is an image of the Grand Falls in Arizona. And you can see active erosion happening here, right? The water is moving material, it is cutting these steps into the rock, it is transporting sediment away from this location, it is dissolving some of the rock, dissolving ions into the water, leaching different minerals into its chemistry, right? And so it is having a profound effect on this region, but really all of the continents on our planet. This is a small diagram illustrating the water cycle. If you've ever taken an intro to geology course, you might have learned a little bit about the water cycle, which is where the water on our continents comes from. We get evaporation off the oceans, we get transport in the atmosphere, making clouds. Those clouds bring precipitation over our continents that falls as rain. That rain is what is causing these kinds of rivers that we see in the background that is doing all of this erosion, and those rivers eventually make their way back into the ocean. Right, so we have this water cycle where water is profoundly affecting all portions of our planet. But again, this is really only a part of the story for the tectonics of the Earth because this is only the surface. And I've told you that there's a lot of water in the interior of the Earth as well. So the surface water cycle, it operates on relatively short timescales for a geologist. So we see water running, we can see a landslide, right? We can see rivers running and moving rocks. If you've ever seen a video of a flood, you see how quickly it can move material, right? So this surface water cycle really operates on pretty short timescales. But that deep water cycle that involves the water that's in the mantle, in the interior of the Earth, it operates on much longer timescales, okay? The mantle convects, it moves material cycles from the top of the mantle to the bottom and back in timescales of about 100 to 200 million years. Water is involved in this cycle through plate tectonics. So we have separate plates that move against each other on the surface of the Earth. Our crust is broken up into these different segments. We have sort of two different kinds of crust on the Earth. We have continental crust, where we live, that is sort of lower density and it sort of floats a little bit higher, right? Which is why we're usually above sea level. And then we have ocean plates, which are made of a denser material. And what happens is that we can get those ocean plates actually subduct. They fall below usually some of these continental regions. And they're taking water with it, right? These ocean plates have been saturated with water for 100 million years before they begin to subduct. So they bring water down into the mantle. Now, if material is going into the mantle in one location, it has to be coming out of the mantle in another location just to maintain the volume of the mantle. And so material comes back up out of the mantle at volcanic centers. So I told you a little bit about hot spots before. There's one sort of where these upward arrows are coming out. There's hot spots producing these ocean islands. And then we also have another major volcanic center called mid-ocean ridges. And this is where oceanic crust is constantly being regenerated. And so this transport of material, the subducting plates bring water into the mantle, and those volcanoes, they bring water back out of the mantle. And this is, again, happening on 100 million years to billion-year timescales. And so this exchange of water between the surface and the interior, it really can affect the ocean size over time. And also, importantly, it affects the rate of plate tectonics, and it affects the overall dynamical evolution of the interior of the planet. Because water has additional really interesting chemical properties in that it modifies many of the properties of the materials in the mantle. So one of the things it does is that it lowers the melting point of rocks. So I apologize for the technical diagram, but this is a figure showing the melting point of rock, which is in the blue line. So what we're seeing is temperature on the x-axis, on this bottom axis, and pressure, so starting from the surface going down to higher pressures as we go from the top to the bottom of this diagram. That blue line is the melting point of rock that doesn't contain any water, that's dry. But if we add water into that rock, in those interstitial spaces I was talking about, as we add water into it, it can cause the melting point of that rock to drop by hundreds of degrees, down to, from 1,800 degrees down to 1,000 degrees, right? So that's a massive, massive change in the properties of that rock. So that makes it easier for the mantle to melt in different areas where there's a lot of water. Water also affects the viscosity of the mantle. So viscosity is really a property of a material that describes how quickly it can move, how quickly it can flow. The classical example, classical comparison is water and honey, right? Water is a very low viscosity fluid. Honey, especially cold honey, is really viscous. If you try to stir honey, it resists, right? Because it is a very viscous material. Well, the mantle also is mixing, constantly moving on these 100 million year timescales. The viscosities are just much, much higher. But when we add water into our rocks, again, it causes that viscosity to lower. And so that can cause the circulation of the mantle to speed up, right? So if we have lower viscosity, we can circulate material faster. And I did put honey on here. Here's my honey bear. And it is, the bottom of my diagram here is 10 to the 12. That's a trillion. Pascal seconds is the unit. And honey is down at about 2 to 10 Pascal a second, right? So honey is a trillion times less viscous than the mantle. So you have a frame of reference. So this property of water affecting the viscosity of the mantle, it can actually lead to a feedback that changes the way that the mantle loses heat to the surface, and that therefore changes the rate of plate tectonics. So what happens is, I'm going to walk you through this diagram over here. So what happens is if we add water into the mantle, that's this term regassing, if we add water into the mantle, that changes the viscosity by lowering it. And what happens when we lower it is that circulation speeds up, right? So our mantle can move faster. And that allows it to transport more heat out of the mantle. So what happens is our heat flux out of the mantle actually increases. And it can occasionally become higher than the actual heat that's being produced in the mantle. So what happens then is our heat production, our heat out of the mantle increases, and that causes the temperature of the mantle to actually decrease. We're losing heat faster, so we're cool faster, so our temperature drops. Temperature also affects our viscosity, so when that happens, the viscosity actually increases. So as we think of, again, of our honey, right? Cold honey is much more viscous than warm honey that you microwaved. So the viscosity goes up, which causes our circulation slows down, and so our heat flux slows down, and we get back to an equilibrium. So this exchange of water in and out of the mantle, it affects how the planet is evolving over long timescales. So we can numerically model this, and this is something that my research group has done in the past, is we can numerically model this and look at what this predicts for how long an ocean will last on the surface of a planet. And in particular, because I am very interested in exoplanets, we're looking at how this depends on the properties of the planet, especially the size of the planet. So one of the studies that we did was to look at this long-term water cycle of water being exchanged between the surface and the interior for planets of different masses. And what we found, the solid line here is for a planet the size of the Earth, and the dashed line is for a planet that's 5 times more massive than the Earth. And this is showing the evolution of the ocean surface coverage of that planet over time. So starting from the time the planet forms, going out to 10 billion years. So Earth is around here at about 4.5 billion years, right? So the surface coverage is very different depending on the mass of the planet. And what we found was that for these massive planets, in fact, if the water all starts in its mantle, there's actually delay in the ocean formation. And so they wouldn't necessarily have oceans very early in their lifetime before it can sort of escape from the mantle towards the surface. Those smaller planets, they have very early ocean formation, and maybe that's really good for the origin of life on those planets. But the water gradually starts moving back into the mantle and not coming back out. So what happens is we have continued subduction of material into the mantle, but at some point the mantle becomes cold enough that we start, the rate of melting and the rate of volcanism that's bringing that water back out slows down. And at some point that water is going to end up being totally trapped in the mantle. If we go out to long enough lifetimes for these planets or small enough planets, this is a bigger problem. So we are interested in these larger planets and the history of their ocean formation because many of the exoplanets that we've found so far that we think have compositions similar to the Earth are larger than the Earth. This diagram over here is showing sort of a histogram of the number of planets we've found at different size ranges. So the most common planet kind that we have found so far is a planet kind that we've sort of called sub-Neptunes. These are planets that are probably not very much like the Earth, right? They're much more like Neptune, hence the very clever naming convention. But the second most abundant type is this second peak here at slightly smaller sizes. But these sizes are still a little bit bigger than the Earth, so something like 1 to 1.5 times the radius of the Earth, which corresponds to this range of about 1 to 5, maybe 7 Earth masses. And those we're classifying, we call them super-Earths. Right now, all we know about them is really their densities, which is that they have densities that would make them similar to the Earth. And so we assume, based on our understanding of the chemistry of the universe, that maybe they have structures and compositions similar to the Earth, and maybe they behave in ways similar to the Earth. Hence, we call them super-Earths. So they are not necessarily habitable planets, just that they have the same bulk composition as us. Getting back to the effect water has on these planets, in addition to this long-term evolution of the amount of water that we have on the surface of these planets, the water also affects the climate of the planets, largely through this cycle we call the carbonate-silicate cycle. And this is really the chemical weathering that we were seeing happen in that image of the waterfall. So what happens is that water in the atmosphere reacts with carbon dioxide in the atmosphere to make carbonic acid. And that falls on our continents and it dissolves some of the rock, which it gets transported into the ocean, where it reacts with more of that carbon dioxide to make carbonate minerals. So here's that chemistry in a little bit more detail. We have CO2 dissolving into water that could be directly into the ocean or into rainfall, and making this acid. And we end up with some carbonate ions that react. In this case, we're showing calcium, but it could be some other ions. But that ends up making this mineral called calcium carbonate, or calcite. Our current marine life forms utilize this calcium carbonate to make shells that they use as their homes that they carry with them. But when those marine life forms die, those shells fall to the ocean floor, and they make these limestones, fossiliferous limestones. Now, you can make a limestone without shells, just from direct precipitation of that calcium carbonate from the ocean water onto the ocean bottom. But this is actually where most of the carbon dioxide on the Earth resides, is in carbonate rocks. It's not actually in the atmosphere. If you compare Venus and the Earth, Venus has an atmosphere 90 times more massive than the Earth's, and most of it is carbon dioxide. We think Earth and Venus actually have similar amounts of carbon dioxide, but for Earth, it's all locked up in these carbonate rocks. And that would not be possible without the oceans on our surface, because the ocean really facilitates this reaction. Now, this regulates our climate because this reaction is temperature dependent. So what happens is if we have a slightly warmer climate, what happens is we get an increased surface temperature, which drives more evaporation from our oceans. That produces more precipitation and increases chemical weathering. That chemical weathering is what is removing CO2, so we draw more CO2 out of the atmosphere, and that reduces greenhouse warming from the atmosphere and causes the surface temperature to drop. So we think that this reaction, this carbonate-silicate cycle, serves as sort of a thermostat for planets that have carbon dioxide in their atmospheres and oceans on their surfaces. So that brings me then to the habitable zone. You probably have heard of the habitable zone. It's a concept defined by astronomers, which is defined as an orbital region where liquid water could be stable on the surface of a planet. That doesn't mean that planet has water. We don't know if planets in this orbital region have water. That is related to the sort of the vagaries of planet formation, whether they end up with water or not. But if they are in this orbital region, they would have the right temperatures for water to exist as a liquid on the surface. This diagram is showing how the habitable zone changes. My husband down here in the audience, he made this animation for me. But we're seeing how the habitable zone changes for stars of different masses and how that changes over time. So you can see that our Earth stays nicely in its habitable zone, but our nearest neighbor, Proxima Centauri b, may actually have been interior to the habitable zone early in its lifetime and only later actually moved into that habitable zone, or the habitable zone moved onto it actually. So we think that within this region, if the planet has an ocean on the surface, then the carbonate-silicate cycle will help maintain that sort of habitable clement temperature that we experience here on the Earth. Now, the inner edge of this habitable zone is defined by the runaway greenhouse effect. And the greenhouse effect is related to the fact that water is a very strong greenhouse gas. Now, the greenhouse effect is that some radiation is coming to us from the sun. Some of it gets reflected, but much of it ends up penetrating through our atmosphere to the surface, and it gets absorbed at the surface. And then the surface actually re-radiates that energy from the sun back to the atmosphere, back to space as infrared radiation, so at longer wavelengths. And the water vapor or other greenhouse gases in the atmosphere actually absorbs radiation at those wavelengths and traps that heat at the ground. So in the absence of an atmosphere, the Earth would be a lot colder than it is today. It would be about 50 degrees colder. But because we have an atmosphere that contains some greenhouse gases, that brings our surface temperature up to a very nice habitable range. But if we put too many greenhouse gases in our atmosphere, right, then we get to uninhabitable temperatures on the high end. So what happens is Earth happens to be in the right spot where we would never hit this runaway greenhouse threshold. But if we are closer to the star, then what happens is that there is sort of a feedback effect. Because water is such a strong greenhouse gas, what happens is if there's water present on the surface and we move our planet a little bit closer to the sun, the surface temperature should increase, which should drive some additional evaporation of water into the atmosphere. Water is a greenhouse gas, so that traps more radiation at the ground, which will drive the surface temperature higher, which will lead to more evaporation. So we get this feedback cycle, this runaway effect when we get too much radiation from the star. So that is happening at the inner edge of this habitable zone. So any planet closer to its star is going to be susceptible to this effect. So if we look in particular at these planets that are orbiting small stars, we see this effect where the habitable zone is initially further away from the star, and then it moves closer in. So our nearest neighbor is Proxima Centauri b, and it orbits one of these kinds of stars. And so Proxima Centauri b spends most of its early lifetime actually experiencing this runaway greenhouse effect, where if it has water on its surface, it should actually all be in the atmosphere, driving a very hot surface temperature. And so one of the questions that we as astronomers trying to look for habitable planets is this planet still habitable after going through this prolonged runaway greenhouse effect? So this is another area where my group has done some modeling. And one of the problems is that the temperature actually becomes so extreme because of the greenhouse effect of a lot of water in the atmosphere that it actually causes the surface to melt and can produce a global magma ocean. Like we saw for many planets as they're forming, some of these exoplanets experience a very long extended period of this magma ocean phase. And the star itself is actually, these small stars, one of the problems with them is that they put out an enhanced amount of very strong X-ray and ultraviolet radiation when they're this young and hot. And that XUV radiation can cause the water vapor in the upper atmosphere to decompose into its atoms, into hydrogen and oxygen, and it can give so much energy to that hydrogen that it escapes from the planet. So it's heating that hydrogen up. Now, the oxygen is heavier, and it typically wouldn't escape from a planet the size of the Earth or even a little bit smaller. But if there's sufficient hydrogen escaping, it will drive some of that oxygen along with it just through friction. So with this extended runaway greenhouse period, then one of the fears is that potentially these planets are losing a lot of their hydrogen, which destroys their water. And so maybe they don't have water left over. And in fact, what we think happens is some of these planets will end up with maybe a little bit of water left over. Maybe they lose all of that hydrogen. And what they're left over with is an atmosphere made of oxygen gas, O2 gas. Well, we have O2 gas, right? But O2 gas in our atmosphere is created almost entirely by biology. And we consider it a biosignature, a gas that we want to search for on other planets as a potential signature that life is present there. So these planets actually have false biosignatures. This oxygen isn't created by life, right? It's created entirely by this effect from the star. So we've looked a little bit at what kinds of planets might be most susceptible to this abiotic oxygen buildup, and it depends on a variety of factors. One of the factors that we think happens is that it depends a little bit on the amount of water that these planets started with. So more massive water, more water-rich planets will build up significantly more oxygen in their atmospheres. Another effect is the size of the planet. So the bigger the planet is, here yellow means that it's built up a lot of oxygen in its atmosphere. And this is for 1 Earth mass planet versus a 10 Earth mass planet on the far right. And that 10 Earth mass planet, because it's much bigger, it doesn't experience quite the same effect. So we get less oxygen buildup. And so as we're looking for targets to go search for life around other stars, we need to be aware of this false biosignature. And we want to select targets that will allow us to say, okay, well, maybe this planet has oxygen in its atmosphere, but is it really from life, or is it from one of these tectonic geologic processes? So I'm going to stop there. I'm going to just leave my summary slide up there, and I'll be happy to take any questions that you all might have.
Are you optimistic about water-bearing planets out there, given the kinds of planets we found so far? Or does this make you a little more pessimistic about water on the surface of planets?
I'm a little, unfortunately, pessimistic for those planets that are orbiting the very smallest stars. So I didn't touch really at all on the current observations that the James Webb Space Telescope is making, but there are a number of programs that are trying to look at small planets. And one of the fears with these small planets around small stars is that they might have lost all of their atmosphere altogether. Not necessarily that they have those oxygen-rich atmospheres, but that the entire atmosphere has been completely eroded. So much of the early work that is happening with the James Webb Telescope is looking to determine, do these planets even have an atmosphere of any kind? At the moment, determining what kind of atmosphere they have is a little bit trickier, and there are people working towards that. Unfortunately, so far, the few planets that have already been observed with this telescope, many of them do not seem to have atmospheres, or they have atmospheres small enough, thin enough, potentially like Mars, that we can't currently detect them. So there's more observations that will be taken to try to probe that a little bit more deeply. But I am more optimistic, to Andy's question, about water existing and surviving on planets around larger stars. So our star is a G star. I think many of those planets, water would survive. Unfortunately, with our current detection techniques, those small Earth-like planets around stars like our sun are currently out of our observational grasp.
I'll let you go ahead and just follow
Okay.
people in order.
Yeah, please.
Yeah, I was interested at the fact that you were talking about the habitable zone going inwards, where in our solar system, as the sun heats up, the habitable zone is going outwards from the star.
That's right. So what happens is the smallest stars actually take a fairly long time to get fully onto their main sequence lifetime. So they go through this very extended contraction phase where they actually start off hotter, and as they contract, they start cooling down and sort of settling onto that main sequence lifetime. So these small stars, they potentially have lifetimes longer than the current age of the universe. So it takes them a while to get down to that main sequence. And so for some of them, it can take almost 1 billion years for them to get to that point where they're in their stable hydrogen burning phase and no longer contracting. So during that time period, when they're very bright, the habitable zone is a little bit further away, and as they start cooling down through that contraction, the habitable zone moves inward. But you're right, for stars like the sun, during its main sequence lifetime, it's only going to get brighter from where it is now. In fact, we think it's increased in brightness already by 20 to 30% since the sun first formed. And so all of those stars indeed are going to get brighter, and so the habitable zone will start moving slightly further out. Yeah, so it's an interesting difference in the stellar evolution of those different stars. Yeah.
I want to ask, if there is so much water in the mantle of the Earth, then maybe on the moon water is also abundant. So how easy would be to extract water from the mantle? Maybe we don't need to land probes at the polar caps where the ice is. Maybe it's possible to extract water from just dig in the moon and get water.
Yeah, so there's definitely been a lot of recent work on water on the moon, and of course people are very interested in being able to mine it. We think that the interior of the moon is probably relatively dry. It's not as dry as people thought it was 20 years ago, but we do think that it is relatively dry. And the reason for that is probably that, the moon formed probably through a giant impact where some protoplanet, maybe the size of Mars, hit the proto-Earth, and it blasted material off the Earth into orbit, and that material coalesced into the moon. And what we think happened is really that most of the volatiles, the hydrogen and carbon and the things that make up water, ended up collapsing back onto the Earth rather than going into that disk. And any volatiles that did end up in that disk, many of them sort of escaped from the disk because it was a lower gravity environment, and so some of that escaped off into space. So we know from looking at other elements that astronomers call them volatile, but you probably wouldn't think of them as volatile. Things like sodium and potassium, we know that process happened, that things escaped from the disk as the moon was forming. So unfortunately, it's unlikely that there's enough water in the lunar mantle to make it worth the economic effort of trying to mine it. So the more easily accessible stuff is stuff that has been implanted near the surface, potentially by impactors, potentially by volcanic eruptions that helped concentrate it in these sort of permanently shadowed regions around the poles. Yeah.
So this is about the false positives
Yes.
biosignatures. So presumably that means most of the hydrogen has left, so there's very little water finally when you get to an atmosphere that's done by geologic processes. So could you guard against a false positive by looking for water vapor as well as oxygen? Presumably if it's still got some water vapor, then it's not all necessarily a geologic process.
That's a good point. That combination of gases might be a little bit better at distinguishing. But these planets don't all necessarily lose all of their water, especially if they start off relatively water-rich. So if they start off water-rich, they can make these really, really thick oxygen atmospheres that are 10 to 100 times thicker than our own current atmosphere, all of oxygen. But they don't necessarily lose all the water that was in the mantle, and so potentially they could still outgas and form smaller oceans. But it might be these very desiccated oxygen atmospheres. One of the problems is that water in for Earth-like planets is going to actually be relatively hard to detect in the atmosphere because it tends to be confined to the very lowermost layers of the atmosphere, right? So for the Earth, water is not very abundant above about 10 kilometers above the troposphere, and the reason is because it condenses, right? It makes clouds and it rains back out onto the oceans. So as you go up in the atmosphere, the abundance of water actually drops substantially. And unfortunately, it's really that upper atmosphere that we're going to be most sensitive to with things like transit spectroscopy. So that might make it a difficult thing. But if we can, future missions are going to try to actually directly image Earth-sized planets. This is going to be a big challenge, and it's not going to happen for probably decades. But that is one of the goals of a future space telescope, is to be able to directly take a photograph of an Earth-sized planet around another star. And that would be a really good way to try to see if there's water on the surface, and would also be much better at probing the abundance of water in the atmosphere. Another question?
Do we have any sense of the isotopic mix of hydrogen and oxygen on the surface water versus the entrapped water on Earth versus orbital bodies?
That's a great question. So this is one of the ways that people try to probe where the water that Earth accreted came from in the solar system. So we think that, the biggest diagnostic there is the hydrogen isotopes and the relative abundance of deuterium and hydrogen. Other volatiles can also play a role here, nitrogen in particular. But by looking at the deuterium to hydrogen ratio, we can see that Earth's water is very similar in composition to a particular kind of meteorite that we have called carbonaceous chondrites. Those we think are sourced from carbonaceous asteroids in the asteroid belt, which were probably scattered into the asteroid belt by this formation of Jupiter and Saturn. They potentially formed sort of somewhere a little bit further beyond Jupiter, and then were scattered inward. So some people have suggested comets as a source of Earth's water, and that is sort of disfavored now because the deuterium to hydrogen ratio of comets is much, much higher than the Earth's. And there's ways that you can change the deuterium to hydrogen ratio of a planet once you get that water, sort of through atmospheric escape. But you actually have to start with a lower value and then increase it to bring it up to the Earth. So starting off with a larger value than the Earth means that would not work. So comets can't have formed a significant portion of the water that the Earth accreted. Yeah.
Hi. Sorry, this is tall. I have to go on my tippy toes. You mentioned that there were those diamonds that trapped minerals in the mantle, I believe it was. And I was wondering, thank you very much. I was wondering, how we get those, how we find those. Do they come out in, volcanic eruptions, or, how do we find those?
They do. So there's some particular regions of places that are known for diamond mining. So South Africa is one region where there just happens to be a volcanic center that brings up a particular kind of very carbon-rich lava that is sourced at great enough depths that there's a lot of diamonds in it. So that's one of the areas where we tend to find a lot of diamonds that come from deep in the mantle. There's other places around where you can get some of these minerals coming from high pressures as well. So sometimes some of the volcanoes that are fed by these deep mantle plumes can also bring up rocks like this or minerals like this. So Iceland and Hawaii are examples of those kinds of places.
Cool. Thank you.
Yeah. Next question.
You mentioned the atmosphere of Venus and how the oxygen is bound up with the carbon there. With these false positive biosignature oxygen-rich atmospheres, would you tend to absorb that excess oxygen into silicates and other oxides? And does your model parameter space encompass the Venus model?
Right, yes, that's one thing I didn't mention about the model that my group has done is that, in fact, some of that oxygen that gets produced in the atmosphere will react with the mantle. And so that's one way to actually pull a lot of that oxygen out of the mantle. But if the mantle is if that magma ocean is actively solidifying, there's a smaller and smaller volume that it can react with. So we do think, going back to Venus, is that we think that Venus started off with more water than it has now. And we think that because of the deuterium to hydrogen ratio of the little bit of water that's left in its atmosphere, we think that most of that hydrogen escaped into space over some portion of Venus's lifetime. So some people think it happened very early in Venus's history, and some people think it took maybe 1 billion to 2 billion years for Venus to lose all that water. But the question of where that oxygen from that water went is still a very active area of investigation. So it really depends on the timing of when that hydrogen, when the water escaped. So some people think that the hydrogen escaped very early when Venus was in one of these magma ocean episodes during planet formation. And so it would have lost all that water immediately, and then it's relatively easy to draw that oxygen down into the rocks. If the water escape is more gradual, then most of the oxygen must have reacted with the crustal materials, and which would make the crustal materials much more oxygen-rich, and as a potential way to determine which of these models is correct is by going and sort of measuring the composition of the minerals on the surface. Which unfortunately, well, hopefully we have several missions that might be able to do this in the near future. Mm-hmm. Okay, I think there's one more question.
Thank you. I was just wondering if you had a few comments to make about how water might exist on, say, Europa or any of the other planets, satellites circulating Jupiter and Saturn.
Yes, definitely. We think all of those satellites are very ice-rich, meaning mostly water ice. Europa, certainly all of the material that we see on the surface of Europa is water ice. And we do have reasons to think that there is a deep ocean under that ice shell. So the ice shell is probably several kilometers thick, several miles thick, if you prefer imperial units. But deep below that, we think that there is an ocean. We think that because Europa actually has a small magnetic field of its own that was measured by the magnetometers on the Galileo mission. And what we think, the way we think that magnetic field is being generated is that the ocean actually is in contact at its bottom surface with the rock at the interior of Europa. And there are materials, elements, ions being dissolved out of that rock and dissolved into the ocean. And so we have this sort of ion-rich ocean that's circulating through Jupiter's own massive magnetic field, and it's creating a tiny little magnetic field that we can detect on Europa. So we think that there is this big subsurface ocean on Europa. And in fact, there's a NASA mission that is going to be launching sometime in 2024? I don't actually, yes, somebody knows the answer to this. So there's a mission that is going to Europa to try to learn more about its ocean from orbiting the system. Yeah, but we do think all of the other moons of Jupiter are also relatively icy, except for the innermost one, Io, which is very volcanically active and has really probably lost any water that it started with to atmospheric escape.
Well, thank you for that wonderful talk, and especially for showing us the variety of worlds that are possible out there. What a rich universe we live in terms of planets. Thank you for showing us. Let's thank Dr. Schaefer. And thank you all for coming. Please drive safely, and we'll see you in 2024.